Right now, as you're watching this, an object from another star system is passing right behind our sun. And here's where it gets truly spine-chilling. NASA has the data, and the James Webb Space Telescope captured something in August 2025 that shatters everything we know about comet behavior. But here's the kicker: most people will never truly grasp the significance of what they're seeing because the details are buried in dense technical language. How is that possible in an era where we're supposedly committed to open science and public transparency? Let me hit you with just one number: the CO2 to water ratio in 3I Atlas coma 8:1. That's the highest ratio ever recorded in comet observation. Not just unusual or surprising, this is history making. Yet when NASA released these findings, they were wrapped in press releases filled with jargon academic papers, so dense they could put anyone to sleep, and public statements that essentially said, it's just a comet move along. But here's what they're not telling you: that ratio doesn't fit any of the models we have for how objects in our solar system form. It hints at something about the origin of this object, how it came to be, and what it's made of that challenges our very understanding of planetary system chemistry. This isn't about wild conspiracy theories. This is about reading between the lines of NASA's own publications and the official story they're feeding to the public, the people who are funding these missions with their tax dollars. There's a significant gap here, one that exists because the data doesn't match the comfortable narrative we've been told since October 2024, when this object was first spotted. If you want to know what NASA's scientists are really thinking behind closed doors about 3I Atlas, if you want to understand why some researchers are calling it a major anomaly, or even a black swan event, stick with me till the end. What we're about to uncover isn't just about one interstellar visitor. It's about how information gets filtered, sanitized, and repackaged between the scientists who discover it and the public who has every right to know. But before we dive in, do me a favor. Hit that like button right now and leave a comment telling me where you're watching from. Because what we're about to discuss isn't just an American or NASA story. This is about how space agencies across the globe handle discoveries that don't fit neatly into the existing frameworks. Let's pull back the curtain and see what's really happening with 3I Atlas. On August 6, 2025, the James Webb Space Telescope aimed its instruments at this interstellar comet. This wasn't just a casual glance. JWST doesn't waste time. Every second of its observation schedule is meticulously planned months in advance, with telescope time highly contested among scientific projects. The fact that JWST was assigned to observe an interstellar comet speaks volumes. It means scientists wanted in-depth spectroscopic data, and they wanted it so badly that they justified using humanity's most advanced space telescope. What came back from that session would completely change the conversation. The near-infrared spectrograph detected a coma, that hazy cloud of gas and dust surrounding the comet's nucleus, which was overwhelmingly dominated by carbon dioxide. When I say dominated, I mean the CO2 to water ratio was 8:1. For every molecule of water vapor detected, there were 8 molecules of carbon dioxide. Let me put this into perspective for you. Typical comets from the Oort cloud or Kuiper belt show the opposite ratio. Water is the dominant volatile. This is the substance that sublimates from the comet's surface as it approaches the sun. Carbon dioxide, though present, is a secondary component. An 8:1 ratio flips that idea entirely. NASA did mention this finding in their press release, and they published the data in the Astrophysical Journal. The numbers are there for anyone to read. But here's where the communication gap begins to emerge. Those press releases didn't bother to explain what this ratio really means. They didn't walk the public through its implications. And once you understand what creates a CO2-dominated coma, you can't help but ask some uncomfortable questions about where 3I Atlas came from and how it formed. NASA scientists have put forward two possible hypotheses to explain this composition. Here's where it gets tricky. The press releases present these as equally plausible, but the evidence might actually favor one over the other. Hypothesis: 3I Atlas formed in a protoplanetary disk far from its parent star, where temperatures were cold enough for CO2 ice to condense more readily than water ice. This would require specific conditions that are uncommon but theoretically possible. Hypothesis 2. The comet formed in a more typical region, but was exposed to extreme radiation from its host star or nearby stellar companions, which selectively stripped away the water ice, leaving a CO2-rich shell behind. Both hypotheses are still on the table, but when you dig deeper into the data, one of them might be more likely than the other. And that's the part that's not being communicated clearly. Both explanations require unique conditions. Neither suggests that this is a typical comet, and that's the key point NASA isn't emphasizing. Whether you lean toward hypothesis 1 or 2, you're dealing with an object that didn't form under typical conditions. It's an outlier, an anomaly. And when you combine this with the other data we've gathered, the anomalies start to pile up, raising suspicions about what else may not be clearly communicated. The James Webb Space Telescope data revealed more than just the gas composition. For one, the water ice grains detected in the coma were smaller than 1 micrometer, extremely fine like powder. There's also evidence suggesting the ice structure might be amorphous rather than crystalline. What does this mean? It means this ice didn't undergo the usual thermal processing that most solar system comets experience. Amorphous ice forms at extremely low temperatures and remains amorphous unless heated. If 3I Atlas retained this amorphous ice, it implies the comet spent its entire existence in a cold environment, never coming close enough to a star to trigger the transition to crystalline ice, a phase change that most solar system comets undergo when they near the sun. This fits with the idea that 3I Atlas formed in the outer reaches of another star system and was ejected into interstellar space billions of years ago. But then there's the swift observatory detection from mid-2025, and this is where things get interesting in a way that doesn't fit the typical narrative. Swift detected signs of water sublimation happening between 4,000 and 10,000 km from the nucleus. That's far, really far. For context, most comet activity occurs much closer to the nucleus, within a few hundred kilometers. Water doesn't usually sublimate at those distances unless something unusual is happening with the grain size distribution particle velocities, or how sunlight is being absorbed and radiated. NASA's reports acknowledge this observation but brush past the reason why it's strange. They simply file it under interesting finding and move on. Here's what you need to understand. Each of these data points could be explained on its own. Scientists are skilled at that. Give them an anomaly, and they'll come up with a model to account for it. But when you stack these anomalies together, when you look at the bigger picture, you're not looking at a comet that's slightly unusual. You're looking at an object that deviates from the norm in several independent ways, and that pattern of deviation is what should make you sit up and pay attention. The August data also gave us the emission rates. 3i Atlas was releasing approximately 129 kilo of CO2 per second compared to just 6.6 kilo of water per second. That's not a small difference. That's a massive imbalance in outgassing composition. And it immediately raises a question. If this object is releasing gas at these rates, where's the corresponding acceleration? When a comet releases gas, those jets create thrust acting, like tiny rocket engines that push the nucleus in different directions. This is known as non-gravitational acceleration, and every active comet shows it, except apparently 3i Atlas. We'll come back to this in a moment, but keep it in mind, gas emission without the expected acceleration. That's problem number one that doesn't have a clean answer. NASA released this data, they published it, they made the data available, but the framing, the context, and the emphasis on how these findings fit together were carefully managed. Technical accuracy without interpretive transparency, that's the gap I'm talking about. You can't accuse them of lying because the data is right there in the journals. But you can absolutely question whether the public communication gives people the tools to truly understand what they're seeing. And when the implications are this significant, when you're talking about an interstellar object that doesn't behave like anything we've seen before, that gap matters. So ask yourself, if you only read NASA's public statements, would you walk away thinking 3i Atlas is just a mildly interesting comet, or would you grasp that its chemical composition represents a genuine puzzle that challenges our current models? The answer to that question tells you everything about how information flows from discovery to public awareness. Let's go deeper into what we're actually seeing in the spectroscopic data, because the CO2 ratio is just the beginning. On September 12th, 2025, the Spectra Polarimetric High Contrast Exoplanet Research Instrument, SPHEREX, for short, conducted extended observations of 3i Atlas and detected an enormous CO2 coma stretching more than 348,000 kilometers across. To put that in perspective, that's almost the distance from Earth to the Moon. This object is dragging a massive cloud of carbon dioxide as it moves through the inner solar system. That's not normal. Even for CO2-rich comets in our solar system, we don't see comas that extended and dense. But it gets stranger. The Very Large Telescope in Chile turned its instruments toward 3i Atlas in late August and detected cyanide gas, not just trace amounts, measurable quantities of CN radicals in the coma. Cyanide in comets isn't unheard of, but it's also not standard. It signals the presence of organic compounds, carbon-nitrogen bonds, that form under specific conditions. Then there's the atomic nickel vapor. Yes, nickel. The VT detected emission lines consistent with nickel atoms in the gas surrounding this object's nucleus. Now let me explain why nickel vapor should make you raise an eyebrow. Nickel is a metal. It has a high vaporization temperature. For nickel to be present as a gas in a comet's coma, the nucleus must contain nickel-bearing minerals, and those minerals need to be heated enough by sunlight to release nickel atoms into the surrounding space. We've seen this in a handful of solar system comets, but it's rare. This suggests that 3i Atlas nucleus isn't just ice and rock. There's a metallic component, possibly from the core of a differentiated body that broke apart, or from metal-rich grains that accreted during formation. Either way, it's adding another layer to its composition profile that doesn't match the standard model of an icy comet from the outer regions of a planetary system. Then we get to the James Clerk Maxwell Telescope data from early September 2025. And this is where the timeline compression becomes really interesting. Between September 7th and 14th, JCMT measured the hydrogen cyanide production rate from 3I Atlas. Over the course of just 1 week, that production rate tripled in just 7 days. That kind of rapid increase in outgassing activity suggests the nucleus was undergoing significant changes as it approached the sun. Maybe fresh ice was being exposed as surface layers sublimated away. Maybe thermal stress was fracturing the structure, opening up new vents. But whatever the mechanism, the rapidity of the change indicates an object that's responding to solar heating in dynamic, perhaps unstable ways. Here's where the conversation in the scientific community gets quietly uncomfortable. If you read the academic literature, if you dive into the preprint servers where researchers post preliminary findings before peer review, you'll find papers that note this chemical profile doesn't match typical Oort cloud objects. It doesn't match Kuiper belt objects. It doesn't cleanly match the other interstellar comet we've studied in detail, 2I Borisov. Borisov showed a much more water-dominated composition. Its gas production rates, its dust-to-gas ratio, its overall behavior were far more consistent with what we expect from solar system comets. Borisov was strange because it came from another star, but its chemistry was familiar. 3I Atlas, however, is strange because it came from another star, and its chemistry is completely unfamiliar. Some researchers, though this is still a minority view, have begun to ask whether 3I Atlas formed in the same kind of environment that produced Borisov. What if different planetary systems create different populations of comets depending on factors like the star's mass, its metallicity, and the structure of the planetary system? What if 3I Atlas came from a system that was fundamentally different from the one that ejected Borisov? That's a reasonable scientific question. It's the kind of thing you'd expect researchers to explore. But it also means we can't just assume that all interstellar comets will look like the comets we're used to. And this assumption that interstellar visitors will be chemically similar to our own icy bodies may be influencing how these findings are communicated to the public. Let's talk numbers again, because numbers don't lie. In August 2025, when 3I Atlas was still relatively far from the sun, it was producing 129 kilos of CO2 per second and 6.6 kilos of water per second. By mid-September, as it got closer, these rates increased. The hydrogen cyanide production rate, as I mentioned, tripled in just a week. But here's what should concern you. Despite these substantial gas emissions, despite the fact that this object is actively shedding mass and releasing volatiles, there's minimal evidence of the non-gravitational acceleration you'd expect to see. We'll dive deeper into that in the next section, but I'm bringing it up now because it ties back to composition. If the outgassing is predominantly CO2, and if that outgassing is somehow symmetrical around the nucleus, you might not see directional acceleration. But achieving that kind of symmetry is incredibly difficult. Comet nuclei are irregular potato-shaped objects with uneven surface compositions. They rotate and they have active and dormant regions. Getting perfectly balanced outgassing from such an object is almost impossible unless the nucleus is much larger and more massive than we initially thought, which would dampen the effect of the jets, or unless something else is going on that we don't yet understand. The nickel vapor detection adds weight to the hypothesis that this nucleus might be larger and more substantial than initial estimates suggested. If there's a significant metallic component, if the nucleus contains materials that survived differentiation in a parent body, we could be looking at a denser, more massive object than a typical icy and dusty comet. And mass matters because it directly affects how much acceleration you get from a given amount of thrust. A small low-mass comet is easily pushed around by outgassing jets. A large high-mass object barely budges. NASA's public communications mention these spectroscopic findings. They acknowledge the detections, but they don't connect the dots in a way that highlights the strangeness. They present each finding as an isolated data point. We detected CO2, we detected cyanide, we detected nickel. What they don't say clearly is that these findings, when put together, paint a picture of an object that doesn't fit our existing models, and we're not entirely sure how to explain it. That second statement is accurate. It's honest. It's what the science actually shows, but it's not what you'll find in the press releases. And that brings us to the question you should be asking yourself: why is there a consistent pattern of downplaying the strangeness? Is it because NASA doesn't want to fuel speculation? Is it because they're waiting for more data before making stronger statements? Is it because the public communication strategy is designed to avoid panic or confusion? All of these might be true, but they don't change the fact that if you're only consuming the official public-facing statements, you're getting a sanitized version of a much more complex and puzzling reality. And in the age of information, when we have access to the academic papers and independent researchers can analyze the same data, that sanitization becomes glaringly obvious. It becomes a choice. And the choices about what to emphasize and what to downplay reveal priorities. So what are NASA's priorities when it comes to 3I Atlas? That's the question we need to keep asking as we dig deeper. Now let's address the physics problem that's keeping orbital dynamicists up at night. When a comet releases gas, the jets create thrust. This is basic rocket science. The gas molecules shoot out from the surface at high velocities, and by Newton's third law, the nucleus experiences an equal and opposite force. Over time, these forces accumulate and create what we call non-gravitational acceleration. It's not a huge effect, but it's measurable, and it's a signature feature of every active comet we've ever tracked. The acceleration affects the comet's orbit, causing it to arrive at perihelion slightly earlier or later than gravitational calculations alone would predict. We can measure these deviations with high precision, and we use them to refine our models of the comet's nucleus rotation, its active regions, and its mass. 3 Atlas is releasing gas. We know this from direct spectroscopic observation. 129 kiloliters of CO2 per second in August, with production rates increasing as it approached the sun. That's not a small amount. For comparison, some of the most active periodic comets in our solar system release similar amounts of material, and yet the orbital tracking data for 3I Atlas shows minimal to no non-gravitational acceleration. The object is following a trajectory that's almost perfectly explained by gravity alone. How is that possible? There are two main explanations, and neither is particularly comfortable. Explanation 1. The nucleus is far larger and more massive than initially estimated. If the nucleus is 5 kilometers across or more, if it weighs tens of billions of tons, then the thrust from outgassing becomes negligible compared to the object's inertia. It's like trying to push a freight train with a handheld fan. The jets are producing thrust, but the object is so massive that the acceleration is below our detection threshold. This explanation works mathematically, but it raises a new problem. An interstellar comet with a 5 kilometer nucleus is extremely rare. Objects that large are difficult to eject from planetary systems. They're more gravitationally bound. The fact that we detect one in the small sample size of 3 confirmed interstellar objects would be statistically surprising. Explanation 2. The outgassing is almost perfectly symmetrical. If jets are firing from all over the surface in a balanced way, the thrust vectors cancel out, resulting in no net acceleration. This is theoretically possible, but it requires a very specific set of conditions. The nucleus would need to be unusually spherical, or its rotation would need to be aligned in just the right way, or the surface composition would need to be remarkably uniform. None of those characteristics are typical for comets. In fact, most comets are wildly asymmetrical both in shape and composition. Getting perfectly balanced outgassing from such objects is the exception, not the rule. Here's where things get controversial, and I need to be clear about what I'm presenting. In September 2025, Avi Loeb, the Harvard astronomer known for his hypothesis about interstellar objects potentially being artificial, made a comment calling the lack of non-gravitational acceleration a major anomaly. His argument goes like this: if you have significant outgassing with no corresponding acceleration, and if the explanations for that require either statistical improbability or very specific geometric configurations, then you should at least consider alternative hypotheses. Lowe suggested, and I'm quoting here, that this acceleration pattern could be consistent with an object that's using its outgassing for controlled propulsion rather than random venting. In other words, a spacecraft using its volatiles as reaction mass in a directed way. Now, before you jump to conclusions, let me be very clear. Lowe's position is not the mainstream scientific consensus. The vast majority of astronomers studying 3I Atlas believe it's a natural object, an interstellar comet with unusual but ultimately explainable properties. Lowe himself acknowledges that his hypothesis is speculative and that more data is needed. But here's why I'm mentioning it. Lowe's hypothesis is testable. It makes predictions. If 3I Atlas were artificial, if it were attempting to break and enter orbit around the Sun, you'd expect to see specific trajectory modifications as it rounds perihelion. You'd expect the object to maintain activity levels consistent with controlled burns rather than thermally driven sublimation. These predictions can be checked against observational data, and that's how science should work. You propose a hypothesis, even a controversial one, and you test it. The problem is NASA's public communications don't engage with this at all. They don't address Lowe's suggestions. They don't explain why the mainstream view is more plausible. They simply ignore the controversy, which only makes people more suspicious, not less. If the data clearly supports natural explanations, why not say that explicitly? Why not issue a statement that says, we're aware of speculative hypotheses about artificial origins, and here's why our data doesn't support them? That kind of transparency would actually build trust. The silence, however, does the opposite. Now let's talk about the orbit itself. The trajectory of 3I Atlas is remarkable in ways that go beyond the acceleration question. The orbital eccentricity is 6.2. That's hyperbolic, meaning this object is on an unbound trajectory. It came into the solar system from interstellar space, and it will leave again, heading back into the void. Its incoming velocity relative to the Sun was 58 km/s. That's fast, but it's not the fastest interstellar object we've seen. Oumuamua was moving faster. What makes 3I Atlas unusual is its orbital plane alignment. The object's orbit is tilted only 5 degrees from the ecliptic, the plane in which the planets orbit the Sun, and it's retrograde, meaning it's moving in the opposite direction of the planets. That combination, low inclination plus retrograde motion, is statistically unusual. If interstellar objects arrive from random directions, you'd expect their orbital planes to be randomly distributed as well. Some would be tilted at high angles, some at low, some prograde, and some retrograde. The fact that 3I Atlas came in nearly aligned with the ecliptic but moving backward is depending on whose statistical model you use. A several percent level coincidence. Not impossible, not even particularly rare when looking at large sample sizes, but noticeable enough that it's been remarked upon in the academic literature. Some researchers have calculated that the probability of 3I Atlas trajectory combined with close approaches to Venus, Mars, and Jupiter, its ecliptic alignment, and perihelion timing is somewhere around 0.05%. That's 1 in 20,000. Those are lottery ticket odds. Again, to be very clear, low probability events happen all the time. Someone wins the lottery every week. But when you're looking at an object that's already anomalous in multiple other ways, and then you add a statistically improbable trajectory, it's worth asking, are we looking at a cluster of coincidences, or is there something we're missing about how this object moves? The mass estimate is directly tied to the acceleration question. If 3I Atlas is small, under 1 kilometer in diameter, its mass would be in the hundreds of millions of tons. An object that size releasing the amount of gas we observe should show measurable non-gravitational acceleration, but it doesn't. So either the mass estimate is wrong, which means the object is much larger, or the outgassing geometry is extraordinarily balanced. NASA's Hubble observations suggest a diameter range between 0.32 kilometers and 5.6 kilometers. That's a huge range. It exists because we can't separate the light from the nucleus from the light scattered by the coma. When you look at 3I Atlas through a telescope, you see a fuzzy blob. You can't resolve the solid nucleus at the center, so you have to infer its size from brightness and assumptions about reflectivity. And that gives you a very wide margin of error. If the true diameter is closer to 5 or 6 kilometers, you're looking at a mass in the range of 33 billion tons or more, assuming typical comet density. That's massive. It's large enough that the outgassing thrust becomes a small perturbation rather than a significant force. But it also means you're dealing with one of the largest interstellar objects ever detected. And you have to ask, how did something that big get ejected from its home system? Typically, smaller objects get kicked out more easily during planetary migrations or stellar encounters. Large objects tend to stay bound within their original systems. So if 3I Atlas is large, its presence here is itself a puzzle. This is the kind of nuance that gets lost in press releases that simply say, interstellar comet passes through the solar system. Technically true, but completely uninformative about the actual science. And that gap, the space between what's technically accurate and what's meaningfully transparent, is where distrust grows. Because people aren't stupid. They can sense when they're being given the sanitized version. They might not have the technical background to articulate exactly what's missing, but they feel it. And that feeling drives them to seek alternative explanations, alternative sources of information, some of which are responsible and some of which are not. NASA could short circuit that entire process by being more forthcoming about the genuine puzzles in the data. But they're not, and that's a choice. On October 13th, 2025, 3I Atlas made its closest approach to Mars, passing within 0.9 astronomical units of the planet, about 28 million kilometers. In astronomical terms, that's close enough that spacecraft orbiting Mars had an opportunity to observe it. The European Space Agency's ExoMars Trace Gas Orbiter did exactly that, using its color and stereo surface imaging system, or CASIS. For short, the orbiter captured images of 3I Atlas during the flyby. This was not a trivial observation. CASIS is designed to image the Martian surface at high resolution, optimized for bright targets in reflected sunlight. 3I Atlas, even at closest approach, was 50,000 times fainter than the surface features CASIS normally photographs. To image something that dim, the instrument team had to use 5-second exposures, which is long for a spacecraft-mounted camera. Longer exposures mean you're more vulnerable to motion, blur-scattered light contamination, and vibrations in the spacecraft. The fact that they attempted it at all tells you how badly the scientific community wanted that data. What did CASIS capture? Coma imaging the extended gas cloud surrounding the nucleus. The images confirmed the coma's extent, its overall morphology, and provided context for the spectroscopic data being gathered by ground-based telescopes. What CASIS didn't capture was a resolved image of the nucleus itself. The nucleus remained unresolved, a point source buried in the glow of the coma. This is the same problem Hubble faced. You can see the cloud, but you can't see the solid body at the center, with enough clarity to measure its size directly. So the mass ambiguity remains. Now here's where the communication gets muddy. The ambiguity surrounding 3I Atlas mass and size remains one of the most significant challenges in fully understanding this object. Despite the advanced instruments and extensive efforts to capture detailed data, key observations, such as those made by the ExoMars Trace Gas Orbiter, did not provide a clear or resolved image of the nucleus. This means that the very heart of the object, the solid body, is still hidden in the glow of its surrounding coma, making it impossible to directly measure the nucleus's size and mass with precision. This unresolved mystery keeps scientists and researchers guessing, and it's exactly these uncertainties that need to be addressed in public communications. The fact that the nucleus remains unresolved is a crucial piece of the puzzle. It's not just about collecting data, it's about the context surrounding that data. The inability to resolve the nucleus means that we are still left with a huge margin of error in our mass estimates, which complicates our ability to understand the full dynamics of this interstellar visitor. But instead of openly discussing these complexities, NASA's public communications often present them as minor or inconsequential. When critical uncertainties like this aren't addressed transparently, it leads to confusion and skepticism among the public, who may feel they're not getting the full story. And that's the problem. If NASA is going to present its findings to the public, it needs to be more upfront about the gaps in the data, the uncertainties in the measurements, and the challenges scientists are still facing. This isn't about admitting failure, it's about fostering a more open and honest conversation about the science. When you look at an object like 3I Atlas, you're not just dealing with a simple anomaly, you're dealing with a complex puzzle that requires careful, detailed analysis. and often a fair amount of patience. There's nothing wrong with not having all the answers, but there is something wrong with presenting only the pieces of the story that fit into an overly neat narrative. What's even more concerning is that these gaps are being downplayed. For example, the public isn't being told that there's still a massive uncertainty regarding 3I Atlas mass. The only estimates we have are based on indirect measurements and assumptions about its reflectivity and brightness. And even then, those estimates vary wildly, anywhere from 0.32 kilometers to 5.6 kilometers in diameter, which leads to vastly different mass calculations. If the object is on the smaller side of that estimate, it would have a mass in the hundreds of millions of tons. But if it's larger, like the 5 kilometer estimate suggests, its mass could be much, much greater, which would change how we understand its behavior in space. NASA could have and should have been more explicit about these uncertainties. The gap between what is technically accurate and what is meaningfully transparent is where distrust begins to grow. People are not naive. They may not have the technical background to articulate what's missing in the narrative, but they feel it. And when they sense that something important is being left out, they begin to seek alternative sources of information, sometimes turning to conspiracy theories or less credible explanations. This is where things get dangerous, because the absence of transparency only fuels further speculation and confusion. So why isn't NASA being more forthcoming? The question of why they don't directly address these uncertainties or openly acknowledge the controversial aspects of the data is crucial. Is it because they don't want to fuel speculation? Is it because they're waiting for more data to make stronger statements? Or is it because the public communication strategy is designed to avoid panic or confusion? While these reasons may be valid to some extent, they don't change the fact that if you're only consuming the official public-facing statements, you're getting a sanitized version of a much more complex and puzzling reality. In today's age of information, where academic papers are accessible to the public and independent researchers can analyze the same data, that sanitization is not only noticeable, but becomes a choice, a deliberate choice about what to emphasize and what to downplay. And these choices reveal a lot about the priorities of the institutions making them. Transparency should be the cornerstone of scientific communication. If NASA were more forthcoming about the genuine puzzles in the data, if they acknowledged the complexities and uncertainties, the public would be far more likely to trust the process and engage with the science in a meaningful way. But as long as they continue to present these anomalies as isolated, unimportant findings, skepticism will continue to grow. On October 13th, 2025, 3I Atlas made its closest approach to Mars, passing within 0.19 astronomical units, about 28 million kilometers of the planet. In astronomical terms, that's close enough that spacecraft orbiting Mars had the opportunity to observe it. The European Space Agency's ExoMars Trace gas orbiter took full advantage of this opportunity using its color and stereo surface imaging system, CASIS, to capture images of 3I Atlas during the flyby. However, this observation was far from trivial. CASIS is designed to image the Martian surface at high resolution, optimized for bright targets reflecting sunlight. Even at its closest approach, 3I Atlas was 50,000 times dimmer than the surface features CASIS typically captures. To image something so faint, the orbiter's team had to use 5-second exposures long for a spacecraft-mounted camera, Longer exposures come with the risk of motion, blur scattered, light contamination, and vibrations from the spacecraft itself. The fact that they even attempted this observation speaks volumes about the scientific community's desire for data. What did Cassie's capture coma imaging the extended gas clouds surrounding the nucleus? The images confirm the coma's extent and morphology, providing context for the spectroscopic data being gathered by ground-based telescopes. But what Cassis didn't capture was a resolved image of the nucleus itself. It remained a point source obscured by the glow of the coma. This is the same issue Hubble faced, being able to see the cloud, but not the solid body at the center. And with that, the mass ambiguity remains. This is where the communication gets muddy. Instead of openly addressing the unresolved questions like the mass ambiguity, the unusual trajectory, and the lack of non-gravitational acceleration, NASA's public statements often focus only on the isolated findings. They present each piece of the data without fully connecting the dots, failing to convey the bigger picture. That 3-eye atlas is a highly anomalous object that doesn't fit our existing models. If NASA were more transparent about these complexities, they could help the public and the scientific community better understand the full significance of this discovery. Instead, by downplaying these issues, NASA risks eroding the trust that comes from clear, honest communication. We might have answered the size question definitively by now, but rover operations are planned far in advance, and retasking for a target of opportunity, like 3-eye atlas, requires flexibility that doesn't always exist in mission operations. So we're left with what we have: ExoMars coma images that confirm activity but don't resolve the nucleus, and a cloud of unverified claims about other observations that may or may not even exist. What bothers me about this entire situation is how easily it could have been avoided. NASA knows that 3-eye atlas is generating public interest. They know speculation is running wild on social media. A single comprehensive briefing where they lay out what's been observed, what hasn't, what the data shows, and what remains unknown would cut through the noise. Instead, we get piecemeal releases, journal papers that take months to publish, and complete silence on the rumors. That's a recipe for distrust. In an era where scientific institutions are already facing credibility challenges and public trust and expertise is fragile, this communication strategy seems almost willfully counterproductive. The fact that we're now in late October 2025 perihelion has just occurred, and we still don't have a clear public statement on what the Mars orbiters and other platforms observed tells you everything about the gap between data acquisition and public transparency. The data exists. It's sitting on servers at ESA, NASA, and in university research groups. Scientists are analyzing it. Papers are being written. But for you and me, for the people who want to understand what's happening with this interstellar visitor, we're left piecing together fragments from press releases, preprint servers, and forum posts. That shouldn't be how this works. The size of 3-eye atlas nucleus is, without exaggeration, one of the most important unknowns in this entire story. And the fact that we still don't have a firm answer 6 months after detailed observations began should tell you something about the challenges of studying interstellar objects. When Hubble pointed its instruments at 3-eye atlas in mid-2025, astronomers were hoping to get a direct measurement of the nucleus's diameter. What they got instead was a range somewhere between 0.32 kilometers and 5.6 kilometers across. That's not a small margin of error. That's a 17-fold uncertainty. It's the difference between a modest, icy boulder and a small mountain. Why such a huge range? Because when you look at 3I Atlas through a telescope, you don't see the nucleus. You see the coma. The nucleus is buried inside that cloud of gas and dust, separating the faint light reflected off the solid body from the much brighter light scattered by the surrounding material is incredibly difficult. Astronomers use models to subtract the coma's contribution, but those models depend on assumptions about the dust size, distribution, the gas production rate, and the scattering properties of the particles. Change those assumptions and your derived nuclear size changes dramatically. If 3I Atlas is on the small end of that range, around 0.5 kilometer in diameter, it fits within the expected population of interstellar comets. Planetary formation models predict that billions of comet-sized bodies get ejected from young star systems during the chaotic early phases when giant planets migrate and gravitationally scatter smaller objects. A half-kilometer comet finding its way to our solar system is statistically reasonable. It's not common, but it's plausible given the billions of stars in the galaxy and the billions of years that have passed. But if 3I Atlas is on the large end, if it's 5 or 6 kilometers across, you've got a problem. Objects that size are much harder to eject. They're more massive, more gravitationally bound to their home systems. Getting them kicked out into interstellar space requires rare dynamical events, close encounters with multiple planets, stellar flybys, or interactions in binary star systems. It's not impossible, but it's uncommon enough that detecting one in a sample size of 3 interstellar objects would be surprising. It would suggest that either we're incredibly lucky or that large interstellar objects are more common than our models predict, which would require revising our understanding of planetary system dynamics. This is what statisticians call a black swan problem. The term comes from the philosophical idea that all swans are white until you see a black one, and that single observation overturns your entire framework. 3I Atlas might be a black swan, a rare object so unusual that its existence forces us to revisit assumptions we thought were solid. Avi Loeb has applied this term explicitly to 3I Atlas, although in his usage, he's also tying it to the artificial hypothesis. Loeb's statistical analysis, and I'm simplifying here, suggests that given the object's size, trajectory composition, and lack of non-gravitational acceleration, the probability of it being artificial is somewhere between 30% and 40%. That's his number. It's based on Bayesian reasoning, where you assign prior probabilities to different hypotheses and update them based on observed data. Most astronomers would put that probability much, much lower. They'd argue that Loeb's priors are too generous toward the artificial hypothesis, and that natural explanations, while requiring some special circumstances, are still far more likely. This is a legitimate scientific disagreement about how to interpret ambiguous data. But here's what frustrates me. NASA hasn't publicly engaged with this debate. They haven't explained why they think Loeb's probability estimate is wrong. If they do think it's wrong, they haven't provided their own statistical analysis of how likely it is that 3I Atlas is a natural comet, given all the observed properties. They've just stayed silent, which allows Loeb's numbers to circulate without counterargument. The mass estimate ties directly to the size question. If the nucleus is small, its mass is low, and the lack of non-gravitational acceleration becomes very hard to explain. If the nucleus is large, its mass is high, and the acceleration puzzle resolves itself through sheer inertia. But we don't know which scenario is correct because we can't measure the size directly. And we can't measure the size directly because we can't resolve the nucleus from the coma. We're stuck in an observational catch-22. There were hopes that the Mars flyby would provide a chance for better size constraints. Spacecraft like ExoMars TGO have higher resolution than ground-based telescopes when observing at close range. But, as we discussed, TGO didn't resolve the nucleus either. The viewing geometry, the brightness contrast, and the instrumental limitations all conspired to keep the nucleus hidden. So the size uncertainty persists. What makes this particularly maddening is that the size directly impacts almost every other question we're trying to answer. How much mass is this object losing per orbit? That depends on size. How long has it been active? That depends on how much total mass it started with, which depends on size. Is the lack of non-gravitational acceleration explainable through natural means? That depends on whether the object is large enough to shrug off the jet forces. Could this object survive multiple passes through the inner solar system? Or is this its first and only close approach to the sun that depends on its structural integrity, which relates to size? You see the problem. Size is the linchpin variable, and we don't have it. NASA's Hubble team published their size estimate with appropriate caveats. They acknowledge the uncertainty. They explain the limitations of the method. If you read the technical paper, it's all there. But the public-facing communications didn't emphasize how consequential this uncertainty is. They presented it as the nucleus is probably less than a kilometer across, without dwelling on the probably or on what it would mean if that estimate is wrong. And that's a pattern. We keep seeing technically accurate statements that omit the context necessary for public understanding. There's another angle worth considering. If you're NASA and you have data suggesting 3I Atlas might be unusually large, do you lead with that in your press releases? Or do you wait until you have confirmation, until you've exhausted every other possibility, before making a statement that will generate headlines and speculation? The conservative approach is to say nothing definitive until you're certain. But that conservatism comes at a cost. It creates an information vacuum that gets filled with speculation, rumor, and alternative narratives. And some of those narratives are going to be less tethered to evidence than NASA's cautious silence. I'm not saying NASA should be reckless with preliminary data. I'm saying there's a middle ground between reckless speculation and opaque silence. And that middle ground is transparent communication of uncertainty. You can say, our current estimates suggest the nucleus is between this size and that size. And here's why we can't narrow it down further yet. If it's on the small end, it means X. If it's on the large end, it means Y. We're working on getting better data. That kind of statement respects the public's intelligence. It provides context. It acknowledges uncertainty without pretending to have answers you don't have, and it builds trust. But that's not what we're getting with 3I Atlas. What we're getting is silence on the hard questions and carefully worded statements that avoid acknowledging how significant the uncertainties are. And that silence, that avoidance, is why people are starting to ask whether there's something NASA knows that they're not sharing. Maybe there isn't. Maybe the silence is just institutional caution, but the effect is the same. Distrust grows. And in an era where trust in institutions is already fragile, that's a problem NASA should be taking more seriously. In September 2025, a paper appeared on ARCIF, the preprint server, where researchers post scientific work before formal peer review. The paper was authored by Ian Hybid, Adam Craw, and Avi Loeb, and it carried a title that immediately raised eyebrows: a pedagogical exercise on close encounters of the third kind. The word pedagogical is key. It signals that the authors are framing their analysis as a teaching tool, a thought experiment designed to illustrate how one might test unconventional hypotheses. But the content of the paper goes much deeper than a classroom exercise. It presents a detailed statistical analysis of 3 atlas trajectory and raises questions that, regardless of how you ultimately answer them, are scientifically legitimate. Here's the core argument. 3i Atlas orbit brings it unusually close to 3 planets in our solar system. It passed Venus at a distance of 0.65 astronomical units, Mars at 0.19 AU, and Jupiter at 0.36 AU. On its own, any one of those close approaches might not mean much, but combined, these planetary encounters are statistically noteworthy. Interstellar objects follow hyperbolic trajectories that intersect the solar system from random directions, and some of those trajectories will inevitably pass near planets by chance. But when you calculate the combined probability of all 3 close approaches happening in sequence, given the object's entry angle, velocity, and orbital plane, the authors of the study arrive at a figure around 0.5%. That's 1 in 20,000. Let me put that in context. If you randomly scattered interstellar objects through the solar system with random trajectories, you'd expect about 1 in 20,000 to pass this close to all 3 planets. That's not astronomically improbable. It's not "this could never happen" naturally territory, but it is uncommon enough that it warrants attention, especially when combined with the other anomalies we've been discussing. The authors of the paper are very careful to state that low probability does not equal impossibility. They acknowledge that unlikely events happen, but they also argue that when you're dealing with an object that already displays multiple unusual characteristics, a statistically improbable trajectory adds to the cumulative case for taking a closer look. Now here's where it gets really interesting, and where the paper shifts from statistical observation to hypothesis testing. The authors note that 3IU Atlas perihelion, its closest approach to the Sun, occurs on October 29, 2025, almost precisely during solar conjunction. Solar conjunction is the period when an object passes behind the Sun from Earth's perspective, making ground-based observation impossible. The Sun's glare drowns out everything in that region of space. If you were designing a trajectory for a spacecraft that wanted to enter the inner solar system unobserved, or that wanted to perform a braking maneuver near the Sun without being easily tracked, perihelion during solar conjunction would be the optimal choice. The paper introduces the concept of a reverse solar orbit maneuver. An orbit maneuver is a technique used in spaceflight where you fire your engines at perihelion, the point of closest approach to the Sun, to maximize the efficiency of your propulsion. Because your velocity is highest at perihelion, the same thrust produces a larger change in orbital energy. It's a well-established principle in astronautics. A reverse orbit maneuver would be using thrust at perihelion, not to accelerate and escape, but to decelerate and remain bound to the Sun, potentially establishing a long-term orbit. The authors calculate that if 3I Atlas were a spacecraft attempting to break into solar orbit, it would need to shed approximately 44 km as a velocity. That's a massive delta VE far beyond what any chemical propulsion system could achieve. But if the object has been venting material for months, if its observed outgassing is actually exhaust from a controlled propulsion system using volatiles as reaction mass, the numbers start to become plausible. Not easy, not simple, but within the realm of theoretical possibility for an advanced propulsion system. Let me be absolutely clear about what this paper is and isn't claiming. The authors explicitly state that they are presenting a hypothesis to be tested, not a conclusion to be accepted. They say, and I'm paraphrasing, that if 3I Atlas were an artificial object attempting to enter solar orbit, its trajectory would look approximately like what we observe. This allows us to make testable predictions. If the object performs maneuvers consistent with braking after perihelion, that would support the hypothesis. If it continues on an unbound hyperbolic trajectory with no further anomalies, the hypothesis is falsified. That's how science works. You propose an idea, you derive predictions, and you test them against reality. The problem, and this is what drives the controversy, is that even framing the question this way feels taboo. The scientific mainstream has a strong allergic reaction to anything that smells like UFO logic or ancient astronaut theories, and that reaction is understandable given the mountains of pseudoscience that get peddled under those labels. But it also means that legitimate edge case hypotheses that are statistically unlikely, but not impossible, get dismissed without serious engagement. Loeb and his co-authors are trying to thread a needle, proposing an unconventional idea while maintaining scientific rigor. And they're getting pushback, not because their math is wrong, but because the idea itself makes people uncomfortable. NASA hasn't responded to this paper publicly, not with a press release, not with a statement, not with a technical rebuttal. There's been no engagement. And you can argue that's appropriate. NASA doesn't have to respond to every preprint that appears on arXiv. But this isn't just any preprint. It's an analysis of an object that NASA is actively studying, authored by researchers at major institutions, and it's generating significant media attention. A response would be valuable. It would clarify NASA's position. It would give the public a framework for understanding why mainstream astronomers think this hypothesis is unlikely. But there's been silence. Let's talk about the planetary close approaches in more detail because they're worth understanding. Venus at 0.65 AU means 3I Atlas passed about 97 million kilometers from Venus. That's not particularly close in planetary terms. Venus's gravitational influence on the object would be negligible at that distance. Mars at 0.9 AU is closer about 28 million kilometers. Still not close enough for a significant gravitational interaction, but close enough that spacecraft in Mars orbit had a viewing opportunity, which we discussed earlier. Jupiter at 0.36 AU is about 54 million kilometers. Jupiter is massive, so its gravitational sphere of influence is large, but at that distance, the effect on 3I Atlas trajectory would be minor. The author's point isn't that these close approaches involved gravitational assists or slingshots. They're not suggesting that 3 Atlas was using these planetary bodies to gain speed or alter its trajectory. Instead, the point is that the combination of the close approaches to 3 planets, Venus, Mars, and Jupiter, is statistically unusual. It's not impossible, but it's a rare alignment of circumstances, especially when combined with the other anomalies we've already discussed. They're not arguing that 3i Atlas used planetary flybys to modify its orbit like spacecraft do. Their point is purely statistical. The trajectory that brings an object near all three of these planets in sequence while also timing perihelion during solar conjunction is uncommon. And if you're looking for patterns that might suggest intentionality, this is the kind of pattern you'd look for. Critics of the paper argue that the authors are cherry-picking, taking an object with an unusual trajectory, calculating the probability after the fact, and then acting surprised that it's low. This is called the Texas sharpshooter fallacy. You fire bullets at a barn, then paint targets around the holes, and claim you're a great shot. The counter-argument from the authors is that they're not claiming the low probability alone proves anything. They're saying it's one data point in a larger constellation of anomalies, and that the cumulative weight of multiple anomalies justifies closer scrutiny. Who's right? That's not a question I can answer definitively. What I can tell you is that this is a legitimate scientific debate, and it's being conducted with mathematics, statistics, and testable predictions. That's good. That's how these things should be hashed out. What frustrates me is that the debate is happening almost entirely in academic circles and on social media with no input from NASA, the institution that has the most data and the most resources to settle the question. NASA could release detailed trajectory analysis. They could publish their own statistical assessment. They could explain what orbital parameters they're tracking and what they consider anomalous. But they're not doing that. And in the absence of that engagement, speculation fills the void. The paper makes one more prediction that's worth noting. If 3i Atlas is attempting to break into solar orbit, optimal Earth intercept, meaning the point at which a trajectory bound for Earth would be established, would occur in late November to early December 2025. That's soon. That's testable. If the object continues outbound on its hyperbolic trajectory, if it shows no signs of orbital modification, the hypothesis is dead. If something changes, if the orbit deviates from predictions in ways that suggest breaking, then we have a genuine scientific mystery that demands explanation. Either way, we're going to get an answer based on observations, not speculation. And that's good. But here's the thing that keeps me up at night about all of this. What if the answer is ambiguous? What if 3i Atlas does something unexpected, but it's subtle enough that it could be explained either as natural, outgassing effects, or as controlled propulsion? What if we're left with dueling interpretations of the same data, with no clear way to decide between them? That's the scenario that would create maximum public confusion and minimum institutional credibility. And based on NASA's communication strategy so far, I'm not confident they're prepared to handle that scenario transparently. If you go to NASA's official website right now and search for information on 3i Atlas, you'll find a page that lays out the basic facts. It tells you when the object was discovered, what its orbital parameters are when perihelion occurs, and that it poses no threat to Earth. All of that is accurate. All of that is technically correct. But if you then compare that public-facing summary to the detailed findings published in academic journals, to the spectroscopic data we've been discussing, to the mass ambiguity in the acceleration puzzle, and the statistical trajectory analysis, you start to see a gap, a significant one. The gap between what's true and what's emphasized, the gap between data and context. NASA's statement says 3I Atlas is a comet. Correct. It says it's on a hyperbolic trajectory. Correct. It says it's been observed by multiple telescopes, including JWST and Hubble. Correct. What it doesn't say is that the chemical composition doesn't match any known class of solar system comet. It doesn't say that the lack of non-gravitational acceleration, despite substantial outgassing, is unexplained. It doesn't say that the size uncertainty spans more than an order of magnitude and that the true size has major implications for how we interpret everything else. It doesn't mention the statistical improbability of the trajectory. It doesn't address the speculative hypotheses that are circulating in the scientific community. These omissions aren't insignificant. They reveal a communication strategy that avoids the hard questions, which in turn fuels mistrust. If NASA were more transparent, it would give the public a better understanding of the complexities involved, and they might even feel more engaged in the scientific process. Instead, we're left with carefully crafted statements that don't provide the full picture. This is what I mean by the communication gap. NASA isn't lying. They're not fabricating data or hiding evidence, but they are presenting the information in a way that minimizes the strangeness, making 3I Atlas sound like just another interstellar comet when the reality is far more complex. You could argue that this is responsible communication, that you shouldn't alarm the public with speculative ideas or unresolved mysteries. But I would argue the opposite. Treating the public like they can't handle complexity is condescending, and ultimately it backfires. People sense when they're being given a sanitized version of the truth, and that sense breeds distrust. Let's look at a specific example. In August 2025, when the JWST spectroscopic data was released, NASA's press release highlighted the detection of CO2 in water, mentioned the unusual ratio, and quoted a scientist saying it was an exciting finding that would help us understand the diversity of comets. That's all true, but compare that to what the actual paper published in the Astrophysical Journal says. The paper notes that the CO2 to water ratio of 8:1 is unprecedented in the observed comet population, and that standard formation models do not predict this composition. The paper discusses the two possible explanations: extreme radiation exposure or an unusual formation location, and it explicitly states that both require special circumstances. That nuance, the acknowledgement that we're looking at something genuinely anomalous, is absent from the press release. Why would you water down your own findings when you communicate them to the public? The most charitable interpretation is that NASA's public affairs team is trying to avoid sensationalism, trying to prevent headlines that scream, "Alien comet baffles scientists." But in avoiding sensationalism, they're also avoiding transparency. They're making editorial decisions about what the public needs to know versus what scientists discuss among themselves. And those editorial decisions shape public perception in ways that may not align with the actual state of scientific understanding. Then there's the IAWN situation, and this one is genuinely murky. The International Asteroid Warning Network, IAWN, is a framework coordinated by the United Nations for tracking near-Earth objects that could pose impact threats. It's activated when an object is identified that requires enhanced tracking and risk assessment. In September and October 2025, reports circulated in astronomy forums claiming that IAWN had been activated for 3I Atlas. Some of these reports cited unnamed sources within European space agencies. Others pointed to increased observation time being allocated to 3I Atlas by various telescopes as evidence of elevated concern. But NASA has never confirmed or denied IAWN activation for 3I Atlas. There's been no official statement. Now, if IAWN was activated, that would be significant because it would indicate that someone, somewhere in the network of space agencies, flagged 3I Atlas as requiring special attention beyond routine scientific observation. It would suggest that trajectory analysts saw something in the orbit that warranted closer monitoring. But without confirmation, we're left with rumors. And rumors are corrosive to trust because they can't be verified or falsified. A simple yes or no from NASA would settle this. The fact that we don't have that answer is in itself a failure of communication. Let's consider why space agencies adopt conservative communication strategies. There are legitimate reasons. Public panic is real. When it comes to objects like 3I Atlas, people often jump to conclusions or feel that they're not being told the whole truth. There's a real concern about how much to say, when to say it, and how it will be received. Keeping things under wraps until more concrete data is available or until a more definitive conclusion can be drawn seems like a safer bet, especially when the implications of the object's true nature are still unclear. But that conservative approach has consequences. It breeds the exact kind of speculation NASA seeks to avoid. In an era where information spreads quickly and freely through social media forums and independent research, the lack of clear communication from NASA doesn't prevent misinformation, it feeds it. When the public is left to fill in the gaps with rumors or incomplete information, trust in the institution begins to erode. The key here is balance. NASA doesn't need to speculate about 3I Atlas origins or make definitive claims about its composition when the data is still being analyzed. But they do need to be transparent about the uncertainties and complexities of what's known. By simply acknowledging the gaps, by saying, we don't have all the answers, but here's what we do know, and here's what we're still investigating, NASA could foster trust and allow the public to engage with the science in an informed way. Instead, by staying silent or minimizing the strangeness NASA inadvertently stokes the very suspicions they aim to quell. It's a delicate balance, but in this case, the lack of transparency has made the situation worse, not better. And as a result, public confidence in their handling of the situation is at risk. If you release information that's misinterpreted or taken out of context, you can create unnecessary fear. We've seen this before with asteroid close approaches that get reported as near misses, even though they're millions of kilometers away. Space agencies also have to maintain credibility within the scientific community. If they hype preliminary findings that later turn out to be wrong, they risk damaging their reputation. So there's definitely a balancing act between transparency and responsibility. But here's the problem: that balancing act has tilted too far toward caution with 3I Atlas. The object is not a threat. NASA has said so repeatedly, and the orbital data supports that there's no risk of impact. So the usual justification for withholding information, avoiding panic, doesn't apply in this case. What we're left with is an object that's scientifically fascinating, genuinely unusual, and yet it's being communicated about in ways that downplay its significance. The only explanation I can come up with for this approach is that NASA wants to avoid engaging with the more speculative interpretations. They don't want to give oxygen to the artificial origin hypothesis. They don't want headlines linking NASA's name to anything that sounds like UFOs or alien spacecraft. That's understandable from a PR perspective, but it's short-sighted. The silence doesn't kill the speculation, it fuels it. When NASA refuses to address Avi Loeb's papers, when they don't explain why mainstream scientists think his probability estimates are too high, when they don't engage with the trajectory analysis or the acceleration puzzle in public forums, they create a narrative vacuum. And that vacuum gets filled by people who are less cautious, less rigorous, and less concerned with evidence. You end up with YouTuber videos claiming NASA is covering up alien contact with social media threads, spinning wild theories, and with a public that doesn't know who to trust. NASA could short-circuit all of that with a single comprehensive briefing. Bring together the scientists who are actually working on 3I Atlas. Have them present the data transparently, including the uncertainties and the unresolved questions. Address the speculative hypotheses directly. Explain why most scientists favor natural explanations, but acknowledge that we're still gathering data. Treat the public like intelligent adults who can handle complexity and uncertainty. That kind of transparency would build trust. It would give people a framework for understanding the legitimate science versus the speculation. But we're not getting that. Instead, we're getting piecemeal press releases and silence on the hard questions. There's another dimension to this that's worth mentioning, the international aspect. 3I Atlas is being observed by telescopes and spacecraft operated by agencies all over the world. ESA, JAXA, national observatories in Chile, Hawaii, the Canary Islands. This isn't just NASA's story, and yet the public communication is dominated by NASA, or more accurately, by the absence of NASA communication. Other agencies have been even quieter. ESA released basic information about the ExoMars observation, but nothing since. There's been no coordinated international statement, no joint briefing, no unified messaging. That fragmentation makes it harder for the public to get a clear picture. What bothers me most is the missed opportunity. 3I Atlas is a genuine scientific discovery. It's the third confirmed interstellar object we've ever detected, and it's displaying characteristics that challenge our models. This should be a moment of public engagement with science, a chance to show people how the scientific method works when you encounter something unexpected. Instead, it's becoming a case study in how institutional caution creates space for conspiracy thinking, and that's on NASA. They have the platform, the credibility, and the data to control this narrative. They're choosing not to. So when people ask me, is NASA hiding something about 3I Atlas? I don't think they're hiding data. The data is published. It's in the journals, but they're hiding context. They're hiding the genuine scientific uncertainty and the real debates happening within the research community. They're presenting a confident, simplified narrative to the public, while the scientists themselves are scratching their heads about multiple unresolved puzzles. That's not transparency. That's management. And when the public realizes they're being managed, trust evaporates. October 29th, 2025, that's today's date. As this video is being released, or perhaps yesterday or tomorrow, depending on your time zone. Right now, 3I Atlas is passing through perihelion. Its closest approach to the Sun is at a distance of roughly 17 million kilometers. That's close. No, not as close as some comets get, but close enough that solar heating will be at its peak. Outgassing should be at its maximum intensity. And if this object is going to do anything unusual, This is when we'd expect to see it. But here's the frustrating part. We can't observe it directly from Earth. The object is in solar conjunction positioned behind the sun from our perspective. The sun's glare makes observation impossible for ground-based telescopes. We're flying blind at exactly the moment when the most interesting things might be happening. It's like watching a thriller, where the screen goes black during the climax. You know something's happening, but you can't see it. But we're not completely blind. There are two spacecraft that might be positioned to observe 3I Atlas near perihelion, the Parker Solar Probe and ESA's Solar Orbiter. Both spacecraft are designed to study the sun from close range, and their orbits take them inside Mercury's orbit into regions where the sun's corona can be directly imaged. Parker's Solar Probe is humanity's closest approach to the sun, swinging within a few million kilometers on its elliptical orbit. Solar Orbiter operates farther out, but its instruments can image the space around the sun in multiple wavelengths. If 3E Atlas passes through their fields of view, and if their instruments happen to be pointed in the right direction, they could capture data that ground telescopes can't. But here's the problem. Neither NASA nor ESA has confirmed that these spacecraft are actively targeting 3I Atlas. There's been no press release saying Parker's Solar Probe will observe the interstellar comet during perihelion. There's been no announcement of coordinated observations, which means either the observation isn't happening, or it's happening, but hasn't been publicly disclosed yet. And given everything we've discussed about NASA's communication approach, either scenario is plausible. If Parker or Solar Orbiter did capture data, we won't see it immediately. Spacecraft data takes time to downlink, to process, to analyze. We might be weeks or months away from any publication, but the fact that we don't even know if the observation was attempted adds another layer of frustration. This is a unique opportunity. 3I Atlas won't be this close to the sun again. It's leaving the inner solar system on an unbound trajectory. This is our one chance to study it at maximum activity, and the public doesn't know if that chance is being taken. There's one more potential observer, the GOES-19 weather satellite. As I mentioned earlier, GOES-19 is a geostationary satellite positioned over the Western Hemisphere, and its cameras can see beyond Earth. During the solar conjunction period, GOES-19's viewing angle might allow it to image 3I Atlas, while Earth-based telescopes can't. But again, no confirmation, no official statement, just speculation. Post-perihelion visibility is more certain. Starting in early November 2025, 3I Atlas will emerge from behind the sun and become visible in the morning sky before sunrise. By mid-November, it will be moving through the constellation Virgo, still bright enough to be observed by amateur astronomers with decent equipment magnitude 10 or brighter. Through December, it will continue outbound, passing through Leo, gradually fading as it moves away from both the sun and Earth. By early 2026, it will drop below magnitude 12, which puts it out of reach for most amateur telescopes. Professional observatories will continue tracking it for as long as possible, but eventually it will fade into the distance and disappear. This post-perihelion period is when we'll get answers to some of the questions we've been discussing. If the object's orbit deviates from gravitational predictions, if there's any sign of trajectory modification consistent with breaking it, will show up in the astrometry data collected during November and December. This is where the hypothesis from the Arrow paper becomes testable. The authors predicted that If 3i Atlas were attempting to establish an Earth intercept trajectory, optimal positioning would occur in late November to early December. That's a specific prediction with a specific time frame. We're going to get an answer. I want to be very clear about something. There is no credible threat. This is a scientifically fascinating object that is being studied carefully, and while the questions it raises are intriguing and unusual, there is no immediate danger to Earth. But how these questions are communicated and explored transparently and thoughtfully will determine how the public perceives both the science and the institutions involved. No space agency, no astronomer, and no one in the mainstream scientific community has suggested that 3i Atlas poses any danger to Earth. Its closest approach to our planet occurred back in July 2025 at a distance of over 120 million kilometers. That's nearly the distance from Earth to the Sun. It's not coming back. Even if its orbit were modified, even if it somehow became bound to the solar system, the trajectory would not intersect Earth. So when I talk about Earth intercept in the context of the Archive paper, I'm referring to a theoretical scenario explored in a thought experiment, not an actual predicted event. But here's where things could get interesting. If 3i Atlas does deviate from its predicted trajectory even slightly, it will create a scientific firestorm. Mainstream astronomers will scramble to explain it through natural means, maybe a sudden outburst from a collapsing subsurface cavity, maybe a fragment breakup that altered the mass distribution, maybe something we haven't thought of yet. Loeb and others will point to it as evidence supporting the artificial hypothesis. The media will go wild, and NASA will be forced to make a statement. That's the scenario I'm watching for, not because I think 3i Atlas is a spacecraft. I genuinely don't know what it is, and I'm comfortable with that uncertainty, but because the response to an anomalous trajectory deviation will reveal a lot about how space agencies handle discoveries that don't fit the standard narrative. Will they be transparent? Will they release the data immediately and let the scientific community debate openly? Or will there be delays, careful messaging, and managed disclosure? There's also the question of the Europa Clipper and Hera spacecraft. Both of these missions were launched in 2024, and trajectory analysis suggests their paths might intersect with 3 Atlas coma or tail during November and December 2025. If that happens, the spacecraft's instruments could sample the gas and dust environment directly. That would be an incredible scientific opportunity. Direct sampling of interstellar material is something we've never done before. The particles and molecules that make up 3i Atlas coma originated in another star system. They carry information about that system's chemistry, its formation, history, and its stellar environment. Getting that data would be a goldmine, but once again, no confirmation from NASA or ESA about whether these spacecraft are being tasked with observations. We're left speculating about opportunities that might be happening or might be missed. And that uncertainty is exhausting. It feels like we're constantly one step behind the information we need to understand what's actually going on. The timeline for the next few months is clear. November through January will be the critical observation window. Observatories around the world will be tracking 3i Atlas, measuring its position with precision, looking for any deviations from the predicted orbit. Spectroscopic observations will continue to monitor gas production rates, composition changes, and activity levels. All of that data will be published eventually, though in astronomy, eventually can mean months or years. Then, sometime in 2026, 3i Atlas will fade beyond observational reach. It will join Oumuamua and Borisov in the small list of interstellar objects we've detected and studied, and we'll be left with whatever data we managed to collect, trying to piece together a coherent explanation for all the anomalies. The question that keeps echoing in my mind is, will we get a clear answer, or will 3i Atlas remain ambiguous in object, with too many unusual features to be dismissed as ordinary, but not quite strange enough to force a paradigm shift? Because that's the outcome that would be most challenging. Ambiguity is hard for humans to tolerate. We want closure. We want to know whether this is just a weird comet or something more. But science doesn't always provide clean answers, especially when you're dealing with objects billions of kilometers away that you can only study through the light they reflect or emit. Sometimes the answer is, we don't know, and we might never know for certain. And if that's where we end up with 3 Atlas, the question becomes, how do space agencies communicate that uncertainty without losing public trust? Based on what we've seen so far, I'm not optimistic. Let's step back from 3i Atlas for a moment and talk about the bigger picture. Because this isn't really a story about one object. It's a story about how scientific discoveries are communicated to the public, about who gets to decide what information is important, and about the gap between institutional caution and public trust. 3i Atlas is just the catalyst, the specific case that makes these broader issues visible. Here's the truth. We're living in an era where interstellar objects are going to become more common, not because there are more of them, but because our detection capabilities are improving. The Vera C. Rubin Observatory, which is set to begin operation soon, will revolutionize sky surveys. It will detect faint, fast-moving objects that previous telescopes would have missed entirely. We found 3 interstellar objects in 8 years: Oumuamua in 2017, Borisov in 2019, and 3i Atlas in 2024. With Rubin online, we might find dozens per year, maybe hundreds. That means the communication challenges we're seeing with 3i Atlas are going to repeat over and over. Each new interstellar visitor will raise questions. Will space agencies handle them with transparency, or will they continue to avoid addressing the hard questions, leaving the public to fill in the gaps with speculation? In the end, 3i Atlas is more than just an object passing through our solar system. It's a test case for how we communicate scientific uncertainty and how space agencies navigate the balance between public trust, transparency, and caution. The outcome of this case will influence how we engage with future discoveries and how much the public can truly trust the institutions that are responsible for studying the unknown. Some discoveries will be straightforward, easily explained by standard comet models, but others will statistically be weird. They'll have unusual compositions, strange trajectories, and unexpected behaviors. And each time that happens, space agencies will face the same choice: be transparent about the uncertainty in the scientific debate, or manage the message to avoid speculation. What I'm arguing, and what I hope is clear from everything we've discussed, is that the management approach doesn't work. It backfires. It creates distrust. It makes people feel like they're being kept in the dark, like there's a two-tier system where scientists get the real story and the public gets a simplified version. In an era where trust in institutions is already fragile, where misinformation spreads faster than corrections, that approach is corrosive. So what should NASA do differently? What should we, as the public, demand? First, transparency about uncertainty. When you don't know something, say so. When the data is ambiguous, explain why. When there are competing hypotheses within the scientific community, present them fairly instead of pretending there's consensus when there isn't. People can handle uncertainty. What they can't handle is the feeling that they're being fed a sanitized narrative. Second, engage with speculative ideas openly. When researchers like Avi Loeb publish hypotheses about artificial origins, don't ignore them. Explain why most scientists disagree. Show your work. Present the statistical reasoning, the evidence, the alternative explanations. Make it a teaching moment instead of a taboo topic. Because silence doesn't kill speculation, it amplifies it. Third, real-time data access. We have the technology to make observational data available to the public as it's collected. Not raw, uncalibrated data that requires expertise to interpret, but processed data with context and explanation. When JWST observed 3I Atlas in August 2025, there's no reason the spectroscopic data couldn't have been released immediately with a briefing explaining what it shows. Yes, peer review takes time, and that's valuable, but preliminary findings can be shared while the formal publication process is ongoing. Other fields do this. Astronomy can too. Fourth, international coordination. 3I Atlas is being studied by agencies and observatories around the world. There should be a coordinated communication strategy, a single authoritative source, where people can get updated information instead of piecemeal press releases from different agencies at different times. Coordinate present a unified picture. Make it clear that the global scientific community is working together and sharing information freely. And finally, respect the public's intelligence. Stop assuming people can't handle complex ideas or ambiguous data. The audience for this kind of content, the people who seek out information about interstellar objects, are not casual observers. They're engaged, curious, often highly educated. They can understand nuance. They can follow statistical arguments. They can tolerate uncertainty. What they can't tolerate is being patronized. Here's why this matters beyond just 3I Atlas. We're on the edge of a new era in astronomy. JWST is operational. Rubin is coming online. The next generation of extremely large telescopes is under construction. We're going to be making discoveries at a pace that previous generations couldn't have imagined. Some of those discoveries will be strange. Some will challenge existing models. Some will be ambiguous enough that they generate legitimate scientific debate. If the communication strategy for each of those discoveries is to downplay the strangeness, to wait months or years before releasing contextual information, to avoid engaging with speculative interpretations, we're going to have a problem. A big one. Because the alternative to institutional transparency isn't ignorance, it's alternative information sources. It's YouTube channels, social media threads, and forums where people piece together fragments of information and fill the gaps with speculation. Some of that speculation will be responsible and evidence-based, but much of it won't. And when that happens, the real scientific discoveries and uncertainties get buried under layers of misinformation, sensationalism, and mistrust. It becomes harder for the public to trust the data and more difficult to separate fact from fiction. This is a critical moment in the relationship between scientific institutions and the public. If space agencies want to maintain credibility and trust, they must change how they communicate about uncertainty. They must engage with the public openly, embrace the complexities of the discoveries they make, and be transparent about the questions that remain unanswered. In the coming years, the world will be looking to space agencies not only for groundbreaking discoveries, but also for how they handle the ambiguity and uncertainty that come with them. The way these agencies communicate could either inspire trust and curiosity or fuel suspicion and misunderstanding. We have a chance to get it right, but only if we're willing to be transparent, honest, and open about the unknowns we encounter along the way. A lot of it won't be, and the public will be left trying to navigate between institutional opacity and speculative noise with no clear way to distinguish credible analysis from nonsense. 3i Atlas has given us a preview of that future. Look at what's happened over the past year. NASA released data, but without adequate context. Researchers published papers raising unconventional hypotheses. Social media exploded with speculation. Some informed, some wild, unverified claims about observations circulated without confirmation or denial. And the public was left confused, uncertain of who to trust, frustrated by the lack of clear information. That's a failure. Not a failure of science, but a failure of communication. So here's what I'm asking you to do. Don't just passively consume the information that space agencies decide to share. Demand more. Demand transparency. Demand engagement with the hard questions. Demand real-time access to data and clear explanations of what it means. And when you see gaps between what's published in academic journals and what's communicated publicly, call it out. Write to NASA. Write to your representatives. Make it clear that you expect better, because this isn't just about satisfying curiosity. It's about maintaining the social contract between scientific institutions and the public that funds them. Your tax dollars pay for these missions, these telescopes, these observations. You have a right to understand what's being discovered. Not a year later, not filtered through press releases written by PR professionals, but in real time with the context necessary to make sense of it. 3i Atlas is still out there, right now, passing behind the sun. We don't know yet what the next few months will bring. Maybe the orbit will be exactly as predicted, confirming it's a natural interstellar comet with unusual but ultimately explainable properties. Maybe there will be deviations that deepen the mystery. Either way, we're going to learn something. The question is whether that learning will happen transparently with the public as active participants, or whether it will happen behind the scenes with carefully managed disclosures weeks or months later. I know which future I want. I want a future where space agencies treat the public as partners in discovery, where uncertainty is acknowledged rather than hidden, where the scientific process is visible in all its messy, exciting complexity. I want a future where my kids can follow along with discoveries as they happen, where they can see how scientists debate and test ideas, where they learn that science isn't a collection of facts handed down from authorities, but a process of questioning evidence and revision. 3i Atlas can be a step toward that future, or it can be another missed opportunity. That choice is in the hands of NASA ESA and the other agencies studying this object. But it's also in our hands because they respond to what we demand. If we accept opacity, that's what we'll get. If we demand transparency, if we make it clear that the old model of managed communication doesn't work anymore, they'll adapt. So stay informed. Follow the scientific literature, not just the press releases. Question what's emphasized and what's omitted, and keep asking, why isn't this being explained more clearly? What aren't we being told? Not because there's necessarily a conspiracy, but because asking those questions pushes institutions toward greater transparency. 3i Atlas is a visitor from another star, carrying with it the chemistry of another world, the history of another system. It's a gift of data, a natural probe that came to us from the void. Let's not waste it by allowing it to disappear into institutional opacity. Let's demand the transparency necessary to understand what it really is, even if that answer is, we're not sure, and here's why. That honest uncertainty is worth more than a confident lie. And right now, with everything we've discussed, with all the gaps between data and communication, we're closer to the lie than the truth. If you made it this far, thank you. Drop a comment telling me what you think. Do you trust NASA's communication on 3i Atlas? Or do you think there's more to the story? And hit subscribe, because over the next few months, we're going to be following this object's post-perihelion trajectory, and you're going to want to see what happens next.